If you all have been taking pictures during your time here that we could share on the workshop site, we put his email up here on the top, so please email photos that you have from the workshop and we will aggregate them together. All right, we're back, everybody. If you have pictures from the workshop, please share them with Rui at the email up here on the upper left, and we'll aggregate photos from the workshop. We would love your photos from the workshop, so please share with us. And right now we have Vincent, who's going to tell us about their operational system.
It's really operational.
Yes. This is a forecast.
Okay.
All right, here we go.
So, thanks everyone for coming back from the break despite the gorgeous weather out there.
And walk.
There's a hawk. Oh, I'm competing with the hawk. Never done that. Okay, so I'll be mostly talking about the genesis of the system you're seeing right here. So this is an actual forecast, valid when I get back, I guess, to Montreal. So this is the Great Lakes area. Montreal is here, so I live here. This is Hurricane Maria, I guess, or tropical storm by now, I assume. So what we're looking at here, so there's the precipitation rate. Here, the brown color is actually stream flow on a log scale, so it's hard to see anything because there's not much happening. There's some action later in the forecast, or earlier, I guess that's the end of the forecast. So after this precipitation line, there's some action, something going on here. You can also see water level anomalies here in the lakes themselves. So this is actually the change in water level from the start of the forecast. So there's a nice sedge developing on Lake Erie here through the forecast. So this is a 2-day forecast. And I pulled a time series at one location of flow and precip, hourly flow and hourly precip. And this is through a web mapping server. So all of the layers are served through a web mapping server, and I'm viewing them through an application called Adagug, developed by the Netherlands Weather Service. So it's not even my viewer that I'm using here. So I'll be talking about the genesis of this system in the next 45 minutes. So going back to slides, it should work. So I put 6 co-authors, but I could have put 20. I work for the Meteorological Research Division of Environment and Climate Change Canada. We added climate change a year ago to our name, so 2 more C's, so it's ECCC. I also collaborators who work for the Meteorological Service of Canada. So we're located in Montreal, and well, actually in Dorval, that's just west of Montreal, very close to the airport. So so that's about here, and we're responsible in this nice concrete building overlooking 10 lanes of highway. Nothing nice like here. Going back there, unfortunately. So we're responsible for weather forecasting, ocean forecasting, hydrological forecasting, and also environmental emergency response, so oil spills, but also air quality and air pollutants in general. So the title of my talk, I didn't emphasize this, is a water cycle prediction system for the Great Lakes and St. Lawrence River. So I want to say what we mean by water cycle prediction. So it's forecasting the processes that impact the continental water cycle at scales of hours to days. So that includes the atmosphere, and in particular precipitation, the land surface, and the continental water surface, and in particular our large lakes that we have in Canada. Our workhorse is our atmospheric model called GEM, for Global Environmental Multi-Scale Model. So this is really a multi-scale model that we run at various scales. So this is our deterministic configuration that goes out to 10 days, currently at 25 kilometers, soon 15, but currently 25. This is used to obtain boundary conditions for a North American domain that has a resolution of 10 kilometers and goes out for 84 hours. And then we have a national domain at 2.5 kilometers that goes out 48 hours. So this is to give you an idea of the scale of our global model here as a function of lead time. This is for the America, so North America, the root mean square error of the geopotential height at 500 millibars. So that's really what meteorologists are after, improving that 500 millibar level. This is RMSE in meters of the height of the 500 millibar as a function of lead time. So in red, this is the error made in July of this year by the Canadian model in red, and then we have the competition. So in green, this is ECMWF. So up to 2 days out, we were just as good as ECMWF then. Slightly worse by about 12 hours until at least day 8, but the scale is very low here. So in the second half of that first week, we're not as good as ECMWF for that month, but we're comparable with other centers. So you have the UK Met here, NCEP as well. This is France. Well, they are probably not very interested by North America. So this is to give you an idea of scale, and so we're trying to bring that curve down. So we're looking for ways to reduce this error. So in the last few years, the main way that we've been trying to that we've been using to reduce that error is through coupling with other models, and in particular with ocean models. So we have the capability of coupling that GEM model to a variety of other models, including a 1D routing model, a 2D river model, a 3D ocean model, the CIC ice model, and the WaveWatch wave model. I'll be first talking about experiments where we've coupled GEM, NEMO, and sea ice, and then we'll add the hydrology. So this is something that was accepted for operational implementation last week. It's a configuration of GEM coupled to NEMO globally at 25 kilometer resolution. So what you're looking at here, so the background color is the ocean temperature so this is Irma and Jose here. This is the uncoupled forecast that was operational at the time, and this is the parallel run where you see the wake of the two hurricanes in the SST, but it also changes the intensity of the hurricanes themselves. So the hurricanes actually become less intense when we activate the two-way coupling. This has impacted the scale of the atmospheric forecast quite a bit. Unfortunately, the ocean forecast is not impacted. It's just as good as it was, not better. But if you look in the tropics, the standard deviation of errors, this is at 850 hectopascal, and this is geopotential. So same type of plot here as a function of lead time. This is in blue the error we had before, in red with the coupling. So starting especially from day 2 or day 3, we have a significant reduction of the error, and that propagates all the way through the stratosphere. That's kind of good news.
a quick question, which parameter have you verified?
Well, we verified all of the standard meteorological variables, and it's positive for all, but this is geopotential height. But we've looked at temperature, dew point, surface pressure, and they're all improved. And the reduction in error typically comes from reduction in busts. So these are large errors in blue made by the operational system, and in red the error made by the system that was running parallel for more than a year. So we're pretty happy about that. So next slide. So the configuration I presented is this one, the 1/4 degree global configuration of NEMO. We have a 1 degree global configuration that is used for seasonal ensemble forecasting as well, so also two-way coupled to GEM. And then we have these regional domains over the Gulf of St. Lawrence and the Great Lakes. So I'll be talking now about this specific domain from which I showed the forecast before. So why do we care about the Great Lakes and water cycle prediction at Environment Canada? It's to help manage transboundary watersheds. So we have many of those that we share with the US. So it's our department that is responsible for not only providing forecasts, so numerical guidance, but also actually managing the dams that are on these rivers and lakes. And the Great Lakes is the more complex most complex of these systems and the largest. So just remind you of where the Great Lakes are. So the Atlantic Ocean here. We have 4 major cities: Montreal, Toronto, Detroit, and Chicago in the basin. It's a major waterway as well, so we can move cargo from the Atlantic. So there are cargo ships leaving Lisbon on a weekly basis and going all the way to Chicago through the lock system. So it's a fairly large system. So if we move the basin to Europe, give something like this. It's the same latitude. I only changed the longitude. So it's like if you could move cargo ship from Nantes to Geneva and then either go to Barcelona or Budapest. So it's a fairly large system. And we have major hydropower dams in the system at the outlet of Lake Superior, Lake Erie, and Lake Ontario that we manage, that we co-manage with the US. This co-management is done by the International Joint Commission, so a binational body, and they're interested to understand what drives changes in lake levels in each of the Great Lakes. So here you're looking at 100 years or so of lake levels, monthly lake levels in each of the lakes. So you can see these variations on decadal timescales of lake levels. So the International Joint Commission asked us to develop a model to understand what's driving. So what are the meteorological drivers behind these lake level changes? And to do that, we've looked specifically at evaporation, precipitation, and runoff. So evaporation from the lake, precipitation on the lake, and by runoff we mean all of the tributary flow going into each lake. So from these 3 terms we can compute what we call net basin supply. So what is net basin supply? It's precipitation from the lake minus evaporation plus the tributary flow going directly into that lake. That does not include inflow from upper lake or outflow to the lower lake. What's interesting is that you can actually compute net basin supply from changes in storage. So as a residual, you can take change in storage from by just monitoring the elevation of the lake and monitoring the outflow and inflow. So you can compute that NBS term. So this you can observe from water levels, essentially. And you can compute it from a model that gives you P, E, and R. So we can compare the two. That's what we did. So to compute P, E, and R, we took our GEM model. So we took essentially short-term forecasts of our GEM model, which includes a land surface scheme. So we took the runoff from that land surface scheme, routed it to the outlet using the WAF-route model, and also we used an open ocean bulk formula to get the evaporation. So the atmospheric model gave us P, the bulk formula gave us E, and the routing model gave us R. And we plotted that for the various lakes. So here I'm showing monthly totals of and net basin supply, so P minus E plus R for Lake Superior here, and this is Lake Michigan. So in black are the observations from the lake level, so this is the residual method, and in orange is what the model gave us out of the box. So fairly high correlation, we were fairly happy, but when you look at the cumulative NBS over a period of 5 years, there was quite a bit of bias. So we wondered where that bias came from. So the first thing we thought, well, our preset must be wrong. Preset from an atmospheric model, what is it worth? So instead of using the model preset, we used precipitation analysis. So this is the Canadian precipitation analysis product. In short, Kappa. This is a North American product, fairly seamless at the borders. You shouldn't be able to see the Canada-US border. We're fairly proud of that in the interpolation. So we used that instead of our GEM preset, and it made almost no difference to the cumulative. So either the precipitation was already good or the analysis was just as bad as the forecast. Yes.
Can I ask what exactly your cumulative is? The integral in time? Or
integral in time. Yeah, so it's just the sum of these.
I can tell you that this is an error that is due to the time difference.
What do you mean?
So, I mean, time integration, but we can talk more.
I'll explain where the bias, we found where the bias comes from.
Yeah, but it's really difficult to find out the integral in time.
But you mean from the observation?
Okay, later. Sorry.
So this is just a sum of these 60 numbers here. So it's not an artifact. This was a bias in the model. So after looking at precipitation, we looked at evaporation. So in the Great Lakes, most of the evaporation actually occurs in winter. So we have very cold air temperature and dry. So we have dry, cold air entrained over the lakes, saturating and moving out of the lakes, creating bursts in evaporation. So in order to figure out if our evaporation was any good, we, in collaboration with NOAA, we installed a set of flux towers on the lake. So these are, the first one, Standard Rock, was installed in 2008 and is still running. And the data is available for testing evaporation models. So what we found looking at our modeled evaporation in green here, this is half-hourly evaporation. Compared to observations in black, this is just showing over a 2-week period, but that we had a systematic overestimation of the evaporation, sometimes by 100%. This is in watts per meter squared. So fairly high evaporation rates that were modeled at 500 watts per meter squared, whereas the observations were more like 250. So we improved the surface roughness parameterization that we use for heat fluxes, and I won't go too much into the details, but we used a different parameterization for momentum and heat fluxes that allowed us to reduce the evaporation rate to that red line much closer to the observation. And doing this, so we replaced our evaporation term by this new computation of evaporation. So instead of a negative bias, we got the blue line here. So we reduced evaporation, since in the net basin supply calculation, it's a negative term. It increased our component NBS, or estimate of NBS. And now we overestimated the observation. So we essentially changed the sign of the bias, but not the magnitude too much. For Lake Michigan, it was much better. But for Lake Superior, where evaporation is even more important, it was still a major issue. So that's when we realized that we needed that two-way coupling, because what's happening if you have, in the model that's providing you the atmospheric forcing, if it's predicting too much evaporation, then in turn it will predict too much precipitation. That it falls back onto you. And because the lakes are so large, it falls back sometimes on the same lake. So we needed that two-way coupling to have, in the atmospheric model, the impact of the improved evaporation parameterization. So that's when we turn to two-way coupling. So we, instead of just running the land surface model offline, we reran the atmospheric model with the improved surface roughness parameterization. That created a major change in the precipitation field. So here it's just over 1 month in winter, the difference in the precipitation total between the two runs, where we have changed the surface roughness. So the magnitude of the change is on the order of tens of millimeters per month over the lakes themselves. And it can also be felt a bit downstream of the lakes themselves. So that closed the water budget for us over these 5 years quite well, as you see. So that's when we were convinced that we really needed to go towards two-way coupling. Because we work in a very integrated way, so we use the same model for these regional studies and for global forecasting, we actually implemented that change in the lake evaporation parameterization in our global model, and saw a fairly significant change in the latent heat flux over the Gulf Stream. So here is before the change to the evaporation parameterization. This is after, and this is a comparison to OA flux, which is not directly an observation, but it's a reference. So we had a major reduction of the evaporation in the Gulf Stream, which translated into better weather forecasts. So that solved, say, the problem of understanding the changes in water levels at the monthly time scale, but there are other problems in the Great Lakes. So the levels of the lakes can change by meters in a matter of hours due to storm surge. So wind-induced surge and sedge on the lakes. This is Lake Erie here, in a matter of a few hours, going up by 3 meters at one end. So we wanted to capture these changes in water levels at very short time scales. And for that, we implemented the NEMO ocean model over the lakes at 2-kilometer resolution. So this is just an animation showing you an event on Lake Michigan. So, and this is a time series over 48 hours of water level in Chicago, in this case going up by about 80 centimeters. And in blue, the forecast 2 days out. So the system works actually quite well to forecast these anomalies in water level. A nice feature of NEMO is that because it includes the CICE ice model, it can now advect and grow ice over the lakes in each forecast, during each forecast. And over a lake like Lake Erie, as you can see, so this is an animation over a 2-day period, the ice cover can change quite dramatically, which of course reduces the evaporation and the precipitation quite a bit, so influencing the local weather. So we wanted to see how much of an impact we had on the weather forecast through this, mostly this advection and growth of ice. And it translated into an improvement in the bias of about 1 degree Celsius at night and 0.5 degrees Celsius during the day in the temperature forecast, and a small improvement of about 0.1 degrees Celsius in standard deviation. So this is bias as a function of heat time, and this is standard deviation as a function of heat time in the surface, in the 2-meter temperature. So the system also produces a stream flow forecasts almost as a byproduct. The objective was really to get the inflows into each of the Great Lakes, but we have stream flow forecasts on a 1-kilometer grid. So I'm here showing an animation of the analysis cycle over a 2-day period in June of this year on a log scale. So it looks like precip, but it's really stream flow. Zooming in, so this is exactly the same event, but on an area just west of Toronto. So you can see, so precipitation is occurring on mostly here on the top portion of the watershed. And then this is the Grand River here. So if you look hard, you can see a flood wave moving through after the event. If you cycle again. So here we have this flood wave moving through. And this one verified very well. So this is at a lower resolution than the national water model in the US. We really are running here the atmospheric model at 10 kilometers and the routing model at 1 kilometer. We implemented this operationally in June of last year, and we had the chance to have in this spring the record high water level, so the highest water level ever recorded on Lake Ontario, which created quite a bit of flooding on Lake Ontario, and also downstream in Montreal. We also had, so in Montreal here, we're at the confluence of the upper St. Lawrence that drains the Great Lakes and the Ottawa River that drains the Ottawa River Basin, and both had record high water levels. So this is the inflow into Lake Ontario in black, and in red is the analysis cycle. So we didn't do too badly. And this is the Ottawa River flow. In this case, this is the analysis cycle. Here, for the Ottawa River flow, we have the observations in black, so hourly observations. In red is the analysis cycle, and in blue, that's the 3-day forecast with no bias correction of any kind here. So the 3-day forecast was almost identical to the simulation. This was mostly snowmelt driven, but there was rain on snow as well for the last peak. So this is snowmelt, and this is snowmelt plus rain on snow. So it worked fairly well. So what we've added recently is a 2D hydrodynamic model for the river itself. So the river is tidal until Trois-Rivières, almost until Montreal. So you can feel the tide of a few centimeters in Montreal, actually. It's mostly, we mostly ignore it, but you can measure it. But in Trois-Rivières, so midway between Quebec City and Montreal, we have Lac Saint-Pierre, which is this lake here, that is tidal. So Lac Saint-Pierre is interesting because it's influenced by both the tides and also by the tributary flow. So this is just the analysis cycle over 1 year, showing water velocity. Here you have the navigation channel here where the velocities are higher, where these cargo ships go through, and the lake with the floodplain that can extend. So there's a highway here. So this year water was about I don't know, 2 miles from the north of the highway. There was water. So it was flooded all the way to here. It's interesting because this is the old national road. So this is the King's Road that was built like centuries ago. And then when they built this highway much closer to the lake, they built it much too close to the lake. So it flooded all the way to the King's Road.
They didn't use this model for that.
Where does this model come from?
This model was developed at the Université du Québec. This is the Institut National de la Recherche Scientifique in Quebec City. It's H2D2, it's open source. And so it has couvrant découvrant. So you can flood. I don't know how you say in English, but you can go from 0 depth. Wetting and drying. That's right.
What is the resolution?
It's a variable grid, so it goes down to meters where you need it. So this is a finite element model. So going down to Quebec City now, where the tides, the average tide is about 5 meters. We have interesting behavior here on this lake also. So here, so this is, Quebec City is here. There's a bridge over the river right here where the water can go, often it will go 10,000 cubic meters per second up the river, sometimes 12,000 up the river, and then just as much down the river. So you can see this very strong inversion here. And there is also funny stuff going on here around that island. What happens when the tide comes in? So the tide first comes in through that arm. then it will actually flow this way because it's constrained by the flow of the river coming down, and then it manages to push the water up all the way to the lake. That's what it's up. That works quite well. And now a few slides about products that are being asked by users from this 2D model. So we have biologists asking for they want to know which water mass they are sampling. So when they're in the lake, if they take a sample, they want to know from which tributary the water comes from, because there's very little lateral mixing in this river, in this lake. So we can, with tracers, we can compute the fraction of the water that's coming from various tributaries. So this is the Richelieu River tributary, this is the Ottawa River, this is the Upper St. Lawrence, and that's the St. Francois River. So if you add them up, we also use the model to follow pollutants. This is the lateral mixing of water released by the water treatment plant in Montreal. So depending on flows, the stuff goes on one side or the other of the islands in this braided section of the river. So that's also very useful for sampling. Yes, we are using conservative tracers. So I just have a few slides on the advantages of using coupled environmental models for us. We found accuracy gains by improving the representation of the surface, both the water surface, I didn't talk about this, but also the land surface. And not only do we improve our offline simulations, but we put these back into the atmospheric model, and we get improved forcing. We have consistency gains, so the evaporation and evapotranspiration are the same in the atmosphere, the hydrology, the lake, and the ocean model. So we're using the same flux parameterization in all of our models. We have latency gains because now the environmental predictions, since they're not done offline after the atmospheric model, but at the same time, they're ready at the same time. And robustness gains, since we benefit from the same 24/7 support that the weather forecast has had forever. And we have a single land surface model to maintain. So the next steps are to increase the resolution of the atmospheric model from 10K to 2.5K for the coupled system on Great Lakes, increase the resolution of the lake model. We're preparing an upgrade, a major upgrade to the land surface model. We want to improve data assimilation of stream flow observations, but there it's much more fuzzy what we're going to do. So we're still exploring very much. And we want to go to ensemble prediction for that system up to 30 days. We're developing a similar system for the Arctic basin. So we have 1/12 of a degree grid for the Arctic basin for NEMO, two-way coupled to a 2.5 kilometer atmospheric model. And I'm responsible for developing the hydrology portion of it, which is much bigger than the Great Lakes, unfortunately. So for now, I'm focusing on the Hudson's Bay because it's a closed basin and I can see the impact on NEMO, and it's all in Canada. So eventually I have to do all of Siberia, and I don't know how I'm doing that for the next task. So this is just a slide showing while black is a pseudo observation, it's a sum of observed tributary flows to Hudson's Bay from 2007 to 2014. In blue is the simulation from the model, and in red is just a monthly climatology from the same simulation. So we can drive then NEMO either with the climatology, that's typically how it's driven with the monthly climatology, or with the time varying inflows. So I chose to look at the impact in 2010 because that's the year where we were departing the most from the climatology. Actually, the model didn't do very well in blue here compared to observations, but it was further even from the climatology. So the sensitivity is fairly high. So here I'm showing the difference in salinity between the two runs, the one with the climatology for 2010 and the one with the simulated flows. And they're different, but we don't have any measurements, so I don't know
So what do
which
you
is
use as salinity at the river inflow?
0. That's it.
Thank you.
How much, I guess, I assume that the US also has models of each of the waves and stuff.
Not
Or maybe
couple.
not.
So the US has POM installed on all the lakes and FVCOM installed on Lake Erie, and they are deploying FVCOM on the other lakes, but it's not operational yet.
So is there much exchange of information back and forth?
Absolutely. So we talk on a very regular basis with NOAA Glura. So NOAA Glura has still to integrate these different components. So that they have a hydrological model, a legacy hydrological model. They're moving towards more hydro, I think.
It won't go operational in the next version for data sharing reasons, international reasons,
Okay.
things like that. But the domain for the Great Lakes Basin is we're only going to be doing the tributary coast in the lakes. We will not be modeling lakes with conventional water.
Yes. So that's FVCOM eventually. So and they have to talk. So WARF hydro and FVCOM. So eventually we will be comparing notes. We're already comparing our forecasts, our NEMO water level forecast to the FVCOM forecast and to the POM forecast. We're doing much better than POM, but POM is the legacy model. We're on par with FVCOM on Lake Erie. I would say slightly better, except in areas very close to shore, where FVCOM, being a finite volume model, has more details. We just what's your question?
Yeah, well, first of all, congratulations, because this is very nice, also with the NEMO coupling, and you made a statement.
Which was?
That you do not get an advantage by doing the two-way coupling
For the ocean model.
ocean model. So what is your two-way coupling with the ocean model?
So on the global, that statement was about the global coupled system where we have GEM, NEMO, and CICE. So we were already, we were running for many years now, NEMO forced by the atmosphere.
By the atmosphere.
Now it's two-way coupled to the atmosphere model.
Okay.
The atmosphere, so the weather forecasts have improved. That should normally, because it's better forcing, translate into improved ocean forecast. So the signal is possibly there, but we cannot measure it.
Measure it, yeah.
So we have different ocean forecasts, but we don't have enough data to see a difference between the two runs.
What is the resolution of your NEMO?
It's a quarter of a degree. And the atmospheric model is 25 kilometers. So they're comparable resolution. So we're moving to 1/12 of a degree for NEMO and 15 kilometers for GEM. But I don't have any results for that. So we didn't see any obvious benefit of
The two-way
the
coupling.
two-way coupling for the ocean forecasting. But we, in terms of timing, atmosphere, it was improved. But because now NEMO is running at the same time as the atmospheric model, the forecast is really at the same time. So we're gaining a few hours there. We don't have to wait for the atmospheric model forecast. We are coupled every time step.
Thank you.
Other questions?
On the HDB2, so right now, is that just running over selected reaches?
Yes.
Or the high impacts infrastructure?
Exactly. So we'll be running H2D2, for example, for all of the connecting channels between the lakes. So where we feel it is necessary, it's not something that we will implement on all the reaches. Where we want inundation mapping. So Lake Champlain, the Chaudière River, so that's in the works.
So
Areas like that.
Those individual instances are tied into your overall model execution workflow.
Yes.
As soon as the stream flow forecast is available, they can rewrite each of these individual instances.
Exactly. And they can talk back. So that's not implemented yet operationally, but so we have NEMO on the Gulf of St. Lawrence and on the Great Lakes, and each 2D2 will connect the two NEMOs.
Okay. You have one.
We have a single, so the boundary conditions will be two NEMOs at both ends. So,
Is that a big computational problem to see that big with that model, or is it not too bad?
no, it's not too bad. So we actually have two configurations of H2D2. One which has less elements to run faster.
Right.
And then we have a much more detailed configuration that we will run just in emergency mode.
Just a 2D model.
It's a 2D model, so vertically integrated. It's not a 3D model. So we let NEMO deal with areas where the flow is really 3D. And when we feel that it's mixed and a 2D model works, that's where we have H2D2.
Sorry, in fact, I was going to ask, since you show the tides entering the channel,
Yes.
I mean, that there will be, maybe that area, a salt intrusion.
Well, with climate change perhaps, but currently it's really just a pressure wave. So what you're seeing here, what I was showing here, and what's moving up the river to Lake Saint-Pierre is just a pressure wave. So the salt intrusion stops here. So
Yeah, but
here this is fresh water.
you have already, you don't have that. I mean,
What
for
do you mean?
biologists, it's very important, I mean, at least what they tell us, to have the salt for their understanding of
Yes.
ecosystem health issues. So in that part of the river, you have already a three-dimensional flow.
Yes, that's right. But for us, we really wanted the flow. It's also a jurisdiction divide. So when it becomes salted water, it's the Department of Fisheries and Ocean.
Oh.
They take over. So we've pushed the boundary condition downstream just because we had a cleaner boundary condition. But we are really only responsible up here. When it becomes salt water, it's not our problem anymore. So in terms of fisheries, so impact on biology and fisheries. So we're still responsible for ocean forecasting in terms of currents and ice for navigation, even for oil spills. But when it comes to biology, it's another department. So they will be probably implementing LVCON to deal with it.
So in terms of the coupling between the NEMO and the river, so what's the couple parameters?
Here, in terms of which variable, it's coupled by levels. So we take H2D2 provides flows, and NEMO provides the level boundary condition.
Just the velocity? You only pass through the velocity?
NEMO is only providing, it's not even providing velocity, it's
No,
just
no,
providing water
it's a
level.
sea level.
Just
The sea level, yes. The velocity is fairly low. We push you don't see here the boundary condition. It's much downstream so that the velocities were small. So we are getting the storm surge signal and the tidal signal. And that's what we need to drive this river model upstream. So
So is there feedback on the river model?
in terms of water levels, yes. So this pressure wave moves up the river, but there's no salt moving and the ocean model doesn't have a very strong velocity compared to the river model. So as we increase the resolution of NEMO, we'll probably take in the velocity, but not at this time. That was not necessary.
Yeah, what is the vertical resolution of the bathymetry?
Of the bathymetry itself, because the model is integrated in the vertical. It varies widely along the shore. You have LiDAR everywhere, so it's less than the accuracy is more than a foot, or a few inches. It's very good. In the middle of the channel, in the navigation channel, it's also very good because it's surveyed frequently. So same level of accuracy, I would say. But in between, we have more uncertainties. So in these areas that are not surveyed by LiDAR and not in the navigation channel, there's nobody who has the operational responsibility for making the measurement. So we go, when we feel that the model is not doing well, we go with the boat and we make measurements.
Anything else? All right,
Thank you.
So next we have Hugh Lewis. I'm going to be picking that up.
Test. This one.
Okay, afternoon everybody. Hope you can put up with my voice. This is a function of the UK autumn already kicking in. And really what I want to try and do this afternoon is to introduce you to the work that we've been doing on regional coupling in the UK. I thought it'd be helpful to try and go back a step to show you some of our sort of motivations for doing the work and how we've gone about organising that, and then also show you some results. As one of the later speakers, I also, if you'll bear with me, thought it might be useful to try and pull together some of our challenges and kind of pick up on a few things that have been discussed over the last day or so as well. If there's time, so let's see how we go. This is home, by the way, and it sort of illustrates that in the UK, of course, we're a maritime country, and we sit at the interfaces as between ocean, land, and sea. And again, my outline really is some motivations. I'm going to describe this UK coupled system to you, provide some results for you, categorised really on what I call windy days, warm days, and wet days, and then talk about the challenges and future directions. There are lots of similarities between our strategy and the work that's just been presented from Environment Canada, and in a sense, hopefully, optimistically, my presentation is about 5, 10 years behind where Vansel has got to. But in terms of overall strategy, then we are also, as an operational centre, running a number of global models, now increasingly coupled in an ensemble, to provide really the synoptic scale drivers for the weather that's impacting on us, or the ocean predictions that's impacting on us around the UK. And then we have a number of local scale, high resolution systems focused on our area of particular interest. And really out of that, we want to be driving not just what the sort of weather forecast or the ocean state is, but moving towards what that means in terms of the impact and response to those conditions. And of course, we're doing that for the next hour, the next day, months and years into the future. So this is kind of our seamless modelling strategy, and it applies across ocean and atmosphere and surface domains, and we use the same tools essentially across all of those scales. And that's really the context in which our regional work is sitting. So on the global side of things, we have a fairly well established and mature system based on the unified model atmosphere, coupled to NEMO and the CICE model. And that's running right across configurations from sort of IPCC, system modelling applications, and then increasingly through to numerical weather prediction. So here's an example of applying those coupled systems in an NWP context. This is from the global run at 10 kilometres. So this is a typhoon case study in Southeast Asia. So on the left-hand side, you can see what the observed wake was. So you can see that cold wake feature that you're familiar with. And then in this coupled system, you can start to get a handle on that and improve the feedbacks to the atmosphere. So there's been some nice verification work of tropical cyclones in particular out of the global coupled system. So that's now in a kind of research to operations implementation path. So as I say, it's already very mature for climate and seasonal. We have developed a weekly coupled data simulation system, and now really transition towards operations over the next year or so at sort of 10 kilometres deterministic, 20 kilometres ensemble, and then coupled to a course to the ocean, and then a sort of pathway towards increasing the resolutions in the ocean in particular beyond that. So that's a pretty well established and mature approach. For the UK scale, then we've, over the last decade or so, we've invested a lot of resource into the UK scale model, and really in increasing the resolution down to where we are today, which is at this 1.5 kilometre resolution. So on this left-hand side, this is just a movie animation of rainfall out of a 1.5 1.5 kilometre model. In the middle is radar. You can sometimes play spot the difference. Essentially, it's getting the kind of convective characteristics of the rainfall. And then on the right-hand side, then this is showing some output from the ensemble system at these resolutions. So we can kind of consider how we go about improving our forecast skill and use, and sometimes think about it in terms of these kind of potential ways of spending your research effort or your compute resources on resolution, on our use of observations, the use of ensembles, and how far into the future we can keep these systems going. And then also this kind of axis called complexity, and that's really where our coupled work comes in. And there's been a relatively less well explored dimension to date in terms of how we increase our forecast skill and use, and that's where our environmental prediction work has come in. Kind of in the context that really resolution is going to stay about this kind of kilometre scale for a good while yet, and the ensemble size, of course, and its characteristics can improve. But in terms of the next steps, we have to ask where are we going to get increased skill. And so there's then a question mark in the research work to be done about can we improve the skill? So can we increase the quality of our predictions by, as we've done in the global system, by explicitly representing the feedbacks between systems? And then can we improve the use? So the applications, is there new capability that drops out of doing coupled work? And similarly to Vincent's list about more consistency between our systems and increased lead times and so on. So those are kind of the two drivers for us. Can we improve predictive skill and can we improve the applications? So we can ask ourselves the question, are we moving towards coupled prediction for UK operational forecasting? And really by trying to explicitly represent these feedbacks between the systems. It's worth saying on this slide that in terms of our atmosphere, ocean, land surface, wave and biogeochemistry components, then all of these systems are run currently operationally for the UK in various configurations. So in terms of the scope of what we're doing, there's sort of nothing particularly new in this picture. We are already an environmental prediction organisation, but really the opportunity and challenge for us is whether we can make better use of those systems and those configurations to try and improve what we're doing and the value of the outputs that we can provide. Also, maybe worth just noting, of course, that you could build a similar kind of construction diagram for our global system, seasonal systems, and so on. So this, fundamentally, there's nothing particularly new. There's a new application and certainly new challenges in this kind of scheme, but in terms of the logic of why we're trying to do things and what we're trying to do is, I think, very in keeping with the overall strategy. So to try and get into this problem of are we moving towards coupled prediction, we developed this prototype project 2 or 3 years ago now, working in partnership with research institutes across the UK. And really our kind of headline objective was to build and evaluate a first look regional system. So you can kind of ask you can work in PowerPoint land and ask yourselves what might the benefits be, but actually you have to invest some effort to build a system and then start to do research work. And that's the experience that we've had over the last few years on this prototype project. In terms of what that's now delivered, we have a prototype system, which is a unified model atmosphere coupled directly to the dual sand surface model, in which we've put a river flow, river routing component. And then we use the WaveWatch 3 wave model and the NEMO, a NEMO configuration for our shelf model. This picture on the right-hand side shows the domain. Hopefully you can see that in a black outline of where we are. So this is kind of kilometre scale resolution across this domain, looking at the northwest shelf of northwest Europe and focused on the UK. The red box in the middle is where our operational weather forecast model was until earlier this year. And the blue box is where our operational ocean forecast model still is at 7 kilometres. And so really, if you're sort of serious about this coupling work, then there's some initial research done on this red box. Even if you're not an oceanographer, you can appreciate that cutting the North Sea in half is a smart move. And the way it kind of cuts the domain is doesn't provide you with a very good ocean system. So one of the very first things we were doing within the project was, between talking to ocean groups and atmosphere groups and land groups, was to work out where the UK is, and get some agreement about that, and then working out what the kind of least worst domain for all of us was at an affordable level to try and do this coupling work. The kind of, a few years later on this, the nice story is that our operational ocean model will be moving to 1.5 kilometre resolution on this black domain in the coming year. And as I said, our atmosphere has already moved to this extended domain. So our coupling work is now a sort of added value onto systems that have already transitioned to this kind of agreed ocean-atmosphere domain. So even that kind of connectivity between the disciplines has been a really nice byproduct of out of the work we're doing. You can find out more about the system in this GMD paper that's hopefully just about to leave discussions, but there with all the gory details about what we've been doing. The other thing maybe to mention as well is that this is a 2D coupling task, so it's all sort of surface coupling. So if we compare this with some of the headaches that others in the Met Office will be having looking at things like Earth system modelling, so coupling 3D chemistry and so on is a sort of much bigger computational and technical challenge than a relatively, simple coupling task at the surface. So it's a relatively tractable thing to be trying to do. Here's just an illustration of that 1.5 kilometre ocean model. So on the left-hand side is a snapshot of surface currents from our current operations at 7 kilometre resolution. You can see the domains on a slightly different rotation and so on. But this is kind of our kind of coupling system. You can see lots more representation of the internal tides along the shelf break and so on, a lot more sort of eddy variability in this kind of system, which is, I mean, both an amazingly beautiful system to work with, but also potentially quite challenging in terms of how we're representing the feedbacks and trying to evaluate the effect of coupling in these kind of resolutions, as well as giving us some new challenges. In terms of our coupling approach, this gives you just a sort of structure diagram of the various variables that are being exchanged between components. And this currently is being done each hour as a coupling frequency, but we'll start to play with varying the frequency at which we're coupling exchanges. So essentially our wave model is producing a Charnock parameter, so telling us something about the sea surface roughness that's used as a bottom boundary into the atmosphere. So in atmosphere-only mode, then we have to assume a certain value for this Charnock parameter all the time, everywhere. We also then couple the sea surface temperatures and the currents as a lower boundary condition from the NEMO model into the atmosphere and the land surface. So again, in atmosphere-only mode, currently we will fix the sea surface temperatures from the initial analysis throughout the run, even if now that's out to 5 days in the future. And we also assume that the lower boundary doesn't move, so we have 0 currents. As part of this coupling, then, we're also exchanging information about the surface currents and the water levels between the ocean and the wave system. A whole bunch of meteorological parameters in the usual kind of the same information that you need to provide in forced mode into the ocean, and then a new development in the UKC3 system of wave parameters into the ocean, wind forcing into the wave. So we'll sort of explore some of this diagram as we go along. The other thing alongside the kind of code and infrastructure has been to develop this sort of evaluation or research toolkit where we have a number of implementations now of the system in uncoupled mode. So we have atmosphere only, ocean only, wave only. And even within this system, we can now start playing around with things like the resolution of our sea surface temperature, initial conditions, or the resolutions of our meteorological forcing. So we get a good handle of sort of potential sensitivities even in this kind of layer before we go to coupling. And then, of course, we can start playing with various flavors of coupling and the extent to which various parts of our system are joined up before you start to get to the fully coupled system. This diagram is showing where we were at what I'd call the UKC2 configuration. You'll find there's if you look hard enough, there's a missing arrow between the wave and the ocean. So in recent months, that's been one of the main things that we've been developing. And this gives you quite a powerful little system then to start to do some pretty first order research about understanding the sensitivities of different parts of the system to the forcing into the boundary conditions. And again, this is one of the benefits, I think, that going to the fully coupled system tells you a lot more about how sensitive your sort of baseline systems are to some of these assumptions that have been quite happily sitting in operation systems for many years. In terms of science, I think I characterize it in this way that this is all good technical stuff, but really what we're interested in is looking at the impact of momentum exchanges across the ocean surface in particular, and the impact of the wave surface layer in modifying how momentum is exchanged across that boundary. We're interested in the kind of partitioning of the heat budget across the sea surface temperature, the sea surface interface, and then the land interface. In a sense, this is a more well-developed activity and problem through the land surface, atmosphere coupling. And then finally into that, the kind of the water cycle approach and how fresh water is then exchanged and kind of is cycled through the system. Really, and still an ongoing challenge for me is to try and get a consistent flow of water from the sky right through the land surface and out into the sea. And when I can kind of close that loop, as already they're doing in Canada, then I'll be a happy chap. So I just wanted to use those kind of three approaches to show you through some of the results that we've got in our research so far. So let's start with kind of what I might call the windy days and look at some of this momentum exchange stuff. This is a case study, so we've run the system for a 5-day case study from December 2014, which was a strong wind, high wave case with, as you can see, sort of coastal flooding and coastal impacts. So this is a plot on the top left, significant wave height, so waves up to 16 meters or so coming in from the northwest from a very big storm. This plot here is the difference between fully coupled system and then our wind forced only wave model. So you can see that the main, as a snapshot, this is the main impact is a decrease in significant waves when you go to the fully coupled system. So as a kind of sanity check, we can ask whether that response makes sense. And it does if you look at this Charnock parameters. This is, we had a nice introduction to it yesterday, but it really impacts on how the sea surface roughness is treated. And this plot here, basically everything that's red in this diagram is rougher than the assumption that's made in the atmosphere only model, and anything that's blue is kind of smoother. So in this particular case, the wave model is telling us that we've got much larger kind of order twice the constant value of this Charnock parameter. So it's increasing the surface roughness, which in turn feeds back, if we look at the differences in the wind speeds now, you can see this kind of blue band of reduced wind speeds just ahead of where this front is. You can also see a lot of noise in these kind of convective systems when you're looking at differences between one configuration and another. But the basic story here is that we've increased the surface roughness due to the waves, which is fed back onto the winds, and that's then reduced the effective waves when that's the new updated winds are used to force the wave system. If we look at an observation site out in the North Atlantic, so here black is the observations through this case, you can see the storm coming in. Our uncoupled wave run that we started with this grey line over predicts the maximums. And moving towards this atmosphere wave ocean coupled system, we start to really see the impact of the decrease and the increase in surface roughness through that peak period. So this is kind of an encouraging first case study for us. If we look at another site here in the English Channel, where we've got particularly strong currents, we can see for the same event, sorry, there are lots of lines on here, but the thing to try and pick out is that you can see this kind of semi-diurnal signal in the significant wave heights, and this is when the storm comes through. So what we're able to do by adding both the meteorological forcing feedbacks and the impact of surface currents at the coast, we can get both this kind of semi-diurnal tidal effect, but also improve the meteorology and improve the timing and the size of that storm as it comes through. As I say, since that kind of case study, we've added in wave effects into NEMO. We've been working with other groups like HSG and INGV to look at processes like the impact that the waves are having on the surface stress, so extracting stress before it goes into the ocean. The Stokes-Coriolis forcing, so the impact of the wave action on the surface currents, and then also the kind of the energy budgets as waves extract and then add back in waves, add back in energy into the TKE budget. So we've been looking at these kind of processes. It's also helped us to move away from or move beyond the 5-day case study. So now we've run an ocean wave coupled system forced by a global atmosphere for a couple of years or so. Here is a snapshot of the impact on the surface currents. Here comparing our sort of current operational 7-kilometre resolution model. So this is a 3-month mean of currents. And then on the right-hand side is this high resolution system. In terms of the impact of the wave forcing, you can see firstly a pretty consistent pattern between 7-kilometre and 1.5, and a general tendency for this summertime 3-month snapshot to be decreasing the surface currents. This is mostly driven by the effect of the waves in taking out, reducing the wind stress that's going into the ocean. If we look at the sea surface temperatures, then this is a winter case. Again, actually, this is the sort of first go at this kind of analysis, but we see some more significant differences between the 7 kilometre and 1.5. So impact of coupling is not resolution, might depend on the resolution. And then really the kind of main signal that we see is in the summertime when we get a relative warming here in North Atlantic, sorry, in the North Sea. And again, consistent across 7 and 15 kilometres. Again, the main driver here seems to be the kind of partitioning of the surface stress. The relative stress that's acting on the sea surface. Apologies for the kind of noise in this plot. This is looking at the wave predictions over that 3-month period, and just picking out a couple of coastal sites. So in black again is the observations, and really let's find a blue line, and that's going to be one of our global forced runs. In red is then our fully coupled ocean atmosphere wave systems. This is the first time that we've run the fully coupled system over a period longer than 5 days. The first good news is it's pretty stable, and the second good news is doing a fairly sensible job. There are occasions in this time series where we can see there are particular benefits of moving to a fully coupled system. What's kind of challenging in this, of course, though, is finding sort of robust statistics that help demonstrate that what you're really doing is an improvement over. Actually, you can sort of draw a straight line through here and do a pretty decent job. So there's a kind of verification challenge in all of this as well. But certainly encouraging initial signs, I would say, but a lot more work to do. The other thing in this plot, of course, is that the global wind forcing is our current operational setup. So the wave model is very well optimized for that kind of wind forcing. When we change the wind forcing to high resolution, we find in general that we degrade the wave quality. So the coupling is kind of acting against that fundamental feature of the wave system that it tends to degrade with high resolution wind forcing. Here are some outputs from the ocean model over that same month period. And really the headline here, if you can see the kind of grey-blue lines up here, this is our output from our 2-year run with global meteorological forcing. And then in red here is the output from the 1-month run with the ocean wave atmosphere coupled system. So in the case of the ocean, then actually, and particularly the coastal sites here, we get improved predictions by going to the high resolution net forcing. You won't be able to see in here, but we can also look at the effect of the wave. The impact of wave coupling is very secondary to the impact of changing the resolution of our atmospheric forcing. And we can kind of highlight that by looking at all of our observation sites and trying to pick out here over that 1-month period for which run we get our best statistics. So essentially red here is the coupled system with a high resolution atmosphere in it. Blue and grey are the global force. We do a much better job with that high resolution meteorology, particularly around the coasts, and we can substantially improve our relative scores. So green here is good. Let's move on to kind of our warm day cases. So this is a kind of, again, one of our first case studies that we ran. So just a snapshot of the initial sea surface temperatures on a summer's day in July 2014. The difference between these two plots is that on the left-hand side, we would keep this sea surface temperature fixed throughout our case study. On the right-hand side, in our coupled system, then the Nemo Ocean is providing an evolution of the sea surface temperature. If we look at 1 o'clock in the afternoon, we can see a relative warming in the coupled system compared to the fixed SST run of order 1 degree or so in the southern North Sea. The question is, what's the impact of that diurnal evolution on the meteorology? And if looking at a transect through our atmosphere model, part of the coupled system across this line here, we can see a relative change in the boundary layer turbulent kinetic energy and an increase in the boundary layer depth. So we saw some other examples of this kind of response yesterday. What's interesting here is that this is a plot of the difference in cloud fraction. So this is showing that in the coupled system, where we've got a more energetic boundary layer, tends to, on this occasion, develop a cloud layer at the sort of boundary layer top in the coupled system that we don't really see. It starts to develop in the uncoupled system, but then quickly dissipates. We get a change in the meteorological conditions through the afternoon due to coupling. Very long. This is sabotage.
Hopefully it's the word.
Really quite a lot of battery. Admire the TK.
So it just runs out.
Yeah, well, and then the bottom came up.
Yeah, we'll do the binder.
Yeah, perhaps if they not store. I think it's a store or bathroom.
It's what's open. Storage.
Escape.
I don't know.
Escape.
So while you are waiting for this, can I ask the difference in cloud? I
Yeah.
don't understand, is it, you said the clouds form more, but then they go away immediately, how do I see?
No,
that?
so this shows you a profile along the bottom with taken through this section here. And in blue we've got the uncoupled model, and in red we've got the coupled system. And so I'm saying, I've said that our uncoupled system has a tendency to develop cloud on this occasion, but I mean of much. This is cloud cover, cloud fraction between 0 and 1. So some clouds develop at the top of the boundary layer, which is lower depth in the uncoupled system. And this is a snapshot of about 1 in the afternoon, but in the uncoupled system, this quickly dissipates, so it doesn't really have much of an impact. In the coupled system, we develop a much sort of stronger cloud layer, and that persists. This feature persists through the afternoon with the coupled system. So essentially, we've heated the surface, we've increased the boundary layer. So you can see here the vertical velocities of the boundary layer compared to between uncoupled in blue and coupled in red. So we've increased the boundary layer height, and we've forced these clouds over the velocity at depth. Then we can look at a bunch of different metrics, and you can find out more about this case in a GRL paper by Jochen Fallmann. One of the main kind of signatures, I guess, of that heating effect at the surface was in the boundary layer depth height. So we're trying to look for kind of metrics and diagnostics that tell us something about the coupling strength. And again, on this occasion, looking at something about boundary layer depth was quite a nice discriminator between uncoupled and uncoupled run. In the coupled system, we can also look at how that variation in the meteorology then feeds back on the ocean. So in the ocean, of course, we have two different representations of what the sea surface temperature evolution was. We have our uncoupled ocean, which is forced by an atmosphere, if we get our heads around this, that doesn't have any cloud in it, so relatively stronger heating. And then we also have our ocean in the coupled system, which is being forced or seeing an atmosphere in which the cloud is developed. So what's the impact of that on the ocean? And you've got this very clear signal in a relative cooling due to the development or otherwise of that cloud layer. And if you then compare against observations, this is a bias. This is our, if we just concentrate actually on the black line, is our ocean run without coupling. So we have a relative warm bias during the afternoon, and that seems to be improved. This is close as I'll say in the coupled case. We've also been looking at a variety of other kind of phenomena, I guess. So one of the classic things to look at would be looking at the sea breeze development. So a good example of ocean atmosphere interaction. So here's a nice case from July 2013 where we developed sea breezes across all sorts of coastal boundaries, and actually you can see all these start to converge. Demonstrates, if you wanted to know, that the UK truly is a maritime continent. This plot here, This plot here shows you the difference in air temperature between the coupled and uncoupled runs. So generally, there's a warming due to coupling, and the main sort of driver of this seems to be that we're just advecting warmer air from a relatively warmer sea surface rather than any particular changes in the dynamics. Having said that, we can look at the relative changes here. This is looking at peak vertical velocity, so at the sea breeze front, and we can see a small displacement between coupled and uncoupled. But in this case, the land-sea contrast, even in uncoupled mode, is very strong. So, it's very hard not to develop the sea breeze. So we want to look at some more wild-shot cases as well to see if this is improving forecasting. Again, the context here is that as we move to higher resolution atmosphere weather models, and we're trying to improve the quality of information, then we start to really be able to worry more and more about, are we getting the afternoon peak temperatures right at a town located somewhere near the coast? So this may not come out in sort of overall verification scores as a kind of rolling annual mean, but in terms of do we get the weather right in the afternoon here, it may well have an impact. Other cases, so we look at coastal fog development. So this is a contrast between a coupled run in terms of visibility, but if we assume here that red blotches are kind of sea fog development, we see much more sea fog for this case in the uncoupled run than the coupled. Again, the uncoupled is relatively cooler. This diurnal warming leads to less fog development. But then we can also use these kind of systems to do some more, rather than going to the fully coupled sort of solution, we can just look at playing around with sea surface temperatures. So here we just keep sea surface temperatures fixed throughout our run. In this case, we've increased by 1 Kelvin. On the left, we've decreased by 1 Kelvin. You can see a very strong response to development of fog or not. And using these kind of more simplified experiments can start to back out some of that complexity that we see in the fully coupled system. And I think it's important to kind of keep grounded in what kind of cause and effect we're supposed to be, we would expect to see using those approaches is useful. We've also been looking at some precipitation cases, and we see some impact of coupling for this particular case, really on the development of this rainfall in the southwest of England. So it's more widespread in the coupled system and may agree better with observations. There seems to be a sort of shift in where the front is going between coupled and uncoupled, some improved kind of verification. It's sort of early days to really get to kind of cause and effect in these precip cases. Also, when you move to the sort of fully coupled idea and linking with the hydrology, then we should be able to see the impact of these kind of changes in rainfall as well through the stream flows and have another sort of monitoring and verification approach. Which kind of brings us on to the rainy days aspect of what we're doing. And really the vision has been well set out for us already this morning, so I won't labour it. But we are hoping and aiming towards moving towards an integrated land surface hydrology simulations as components of both the fully coupled air system global, but also these environmental prediction systems. And there's plenty of wise words written in the press about trying to do that. So for that, in the UK, we're working with the Jules UK land surface scheme, which is a fairly typical land surface scheme used across global and regional applications, with the usual kind of land surface processes included. What we did in the environmental prediction work, though, is to go beyond the surface and subsurface, runoff generation, and then read that, those runoffs across the land surface. The challenge really, though, as again, it's been well stated, that we're aiming for skillful hydrology everywhere, all the time, so we're not sort of necessarily set on a particular application and sort of calibrating our model for that. We're introducing additional model complexity, but also additional constraints. We have to get more things right in the system, and a whole bunch more model parameters and calibration issues. So it's not trivial at all. We're also, moving from essentially a 1D soil feedback process from the atmospheric perspective to a fully 3D connectivity. And Wharf Hydro's got a very nice illustration of the kind of grid connectivity required. Questions about river flow assimilation, and particularly then the balance of that with the surface exchange. So at the moment, Jules is quite well constrained by the atmosphere. It's serving the atmosphere and it's doing a very good job because we get the weather forecast about right, with no constraints at all on the hydrology. That's been one of the main headaches for me over the last few years. Initialization strategy, again, for atmosphere and ocean are fairly well developed. For kind of river flows, less well developed. And Jules, like many land surface models, again, can run online and offline. Research offline is not necessarily, doesn't translate so well into offline mode, into online mode. So many challenges and still very much work in progress. The kind of optimistic note is the building blocks are essentially in place, or as well in place as in most other kind of hydrological modelling systems. So Joules in and of itself can produce you some half-decent stream flows, and there's been some work with our colleagues in the Centre of Ecology and Hydrology to try and improve sort of first order look at parameters for UK and doing this offline work. The challenge for me has then been implementing, so this offline stuff is driven by observations essentially, using slightly different ancillary, slightly different grids, and all the kind of details that you hope don't matter, actually they do. So I've been wrestling with trying to get this implemented in a fully coupled system. I have a nice movie to show you. You'll note the movie of streamflow doesn't have an axis, it doesn't have a scale on it, and the day I can show you the scale will be another happy day for me. But in terms of connectivity of water between sky and sea, we're at least making a start on that. We've got something to work with. One of the kind of interesting challenges of doing this work is fairly basic things like what's the soil moisture. So this illustration here shows you a snapshot of the initial soil moisture that I'm getting in my kind of unified model Joules online run between two different versions of the setup. So this is essentially my UKC3 system, and this is what UKC2 system looked like. The soil moisture is coming from a global analysis that's then kind of downscaled to the UK. I still don't really know what happened between these two versions. I just know they're different. And so even if everything was working beautifully in this system, I've then added a load more subsurface water into my system, just by virtue of new physics, new configurations, new code. So, one of the approaches we're looking at is the data assimilation group have now developed a sort of the UK regional scale version of the soil moisture analysis. And this shows you down the bottom the percentage differences, so basically emphasising differences plus minus 10% from moving from a kind of global reconfiguration to something that's more doing the analysis on the UK grid. So again, there's scope for certainly changes in the hydrology, but we need to pull this right through to improving the initialisation of our soil moisture. This should be flattering to some people in the room, but future progress in the UK is going to be delivered, I hope, through a programme of work called Hydrology, where really it's an appreciation, I think, in the fact that the Joules system has been developed mostly with kind of the atmospheric feedbacks and also the kind of longer-term climate and carbon cycling type effort, with relatively little investment in what the hydrology is doing. And I think more and more that's becoming a limiting factor. So there's an activity of work through the Research Council to try and move working through Joules and really with applications like environmental prediction at the heart of it, but moving on to a more fully developed integrated system. And again, if we get anywhere close to the kind of Wolf hydro experience, we'll be doing well. The other thing just to raise here, of course, is not to lose sight of the fact that in a fully coupled system, then the characteristics of our forcing changes as well. So this is a snapshot of some convective rainfall, all in the high resolution 1.5 kilometre system. But this was our old physics, where we had a phenomenon called globbiness, where all of our convective rain tended to be a bit high, but also too well organised. We have a new convection scheme now in place, and we get a much better kind of distribution of the rainfall. Seeing how this kind of features feed through into the hydrology and whether you can see a kind of a measurable difference in terms of what the stream flows then look like will be very powerful. I think that we can't kind of, again, fixing our coupled system will evolve in time. And as our components get better, then our coupled system gets better. And it's, again, we can't necessarily introduce new skill where we don't have it. So if I've got time, I will sort of ramble through some future directions for us and, again, more challenges that I have, but the good news for me is that we all have them and we can all hopefully share them and make progress. So work for us in the UK is continuing beyond that prototype work through phase 2, so the UKC3 developments and the ocean wave interactions, for example, is one of the first activities we've been doing. But we sort of organise our work basically trying to keep our work in the arrows. So our components improved, but really our research focuses on these 4 aspects of feedbacks between these different systems, and then there's a kind of effort in the technical system development and evaluation of schemes and so on. And so the system itself will evolve over the coming years, but this phase 2 is a kind of 4-year effort. Really going, I guess I'd characterise it that our prototype work was relatively straightforward. We took we took well-developed components, we sort of slammed them together, we ran some case studies and we found that we hadn't fundamentally broken anything. Now in phase 2, I think we have to sort of start teasing those components apart a bit more, looking properly under the hood and finding out, are the feedbacks what we would expect, and how can we now start to get into the detail of, are we doing the right things for the right reason? To what extent are the parameterizations and the different models working with each other, against each other, and so on. So it's kind of into the hard, exciting, detailed work now before we then sort of start to ease those components back together, and that's the phase we're at. But I think it's an important part of what we need to do. In terms of sort of opportunities for ongoing development, then we have more than enough data, too much data. Data is available if anyone wants to share it, to start to continue the evaluation and research. This is a kind of interesting snapshot that passed us by one afternoon and then it's dropped off the agenda again until someone picks it up again. This just shows you evening temperatures over Paris, as it happens, between the fully coupled and the uncoupled system. So it turns out, through some mechanism, our nighttime temperatures in Paris are much changed on this occasion due to coupling. So it'd be really interesting to have a look at what's going on there, what's right, what's the process, is it observable, and so on. So many more sort of observational and evaluation work to be done. We've talked a lot in the last day or so about the land-sea interface, which is hasn't been addressed at all in the UK work to date. This is an illustration from work a few years ago in the National Oceanography Centre about the impact of representing the river outflows on, this is a characterisation of dredging, but essentially showed if you took care of the river outflows, then you find that all the material you dumped into the sea comes up 5 days later back into your river channel. So again, really interested in this meeting to find out what the groups are doing to do a better job at our interface. The other aspect I've talked really about the kind of short days to weeks time scale. So we run these convective scale atmosphere models out for kind of climate change scenarios. And this shot here is from a paper by Lizzie Kendon, which shows you the difference in summertime precip characteristics as viewed in a 12-kilometre kind of regional climate model versus looking at these 1.5-kilometre models that are representing the terrain convective processes much better. So there is appetite as we move towards these high resolution systems to look at regional climate scenarios in an integrated coupled system. And again, if you think about just what the rainfall to hydrological impacts of these kind of changes are, that's work to continue over the next few years. I've focused on the UK, but we have interest elsewhere. So in particular, the Asia Maritime continent, I think, is a good opportunity for consolidating efforts across groups. While the global modelers, we could all sit and we were all looking at the same globe. At the moment, we're all looking at different parts of the world, and we're sort of mandated to be looking at different parts of the world. So exchanging kind of knowledge and best practice and looking at the same part of the world is a challenge for regional modelers relative to the global guys. However, we've been working with the Singapore Met Service to look at a coupled system based on developments that have been going on with the unified model over that region. So really, they pretty much took our coupled infrastructure and have implemented it now for the Singapore region without too much overhead beyond the sort of development work to implement those configurations in the first place. So kind of going back, if you remember, we had a tropical cyclone case from the global model. This is showing you a tropical cyclone case now from the regional system at 4 kilometres. So this is essentially the uncoupled unified model analysis, and in the coupled system, then we get that kind of cold wake system again. So again, kind of early days with that. This is a trace of the minimum pressure through that system. So the analysis is in black here. The lines that dip down here are uncoupled, and we get that reduction in this sort of over deepening. That's again pretty typical from the global cases, but we're now seeing that in the regional system as well. In terms of challenges, then we haven't really talked much about this at all, I'd say, but there's a massive observational challenge and how we evaluate these coupled models. I guess I have an additional challenge at the kind of 1 kilometre scale where sort of to what extent is adding variability, or how can I evaluate that adding variability is doing the right thing or not? And linked to this again is the challenge around data assimilation and initialization that we still need to make progress on. This is also a software engineering challenge. I'm not proposing to go into this, but I can explain it to anybody who wants to. But really, this is showing our kind of parameter space for how quickly or how much compute power we want to throw at the coupled system. And I guess the headline here is that this is the time to do a data integration on this axis. And what this was telling us is that our wave model was the limiting factor in our system as we were with the configuration we were running at. So we couldn't, regardless of how many nodes we threw at the problem, we could only get a day out in, let's say, let's call it a half an hour or so. And therefore, the unified model scales much better. So we could throw lots and lots of compute nodes at it and get our simulations done pretty quickly. But there's really no point at all, because in couple mode, you'd have these systems waiting every hour until the wave model finally catches up with you, and then you can exchange all the information and off you go. So in the coupled system, really the challenge is not as much sort of how much compute power do I have, but how do I balance my components so that we're all working at, kind of in sync, and nothing is there's no inefficiencies, nothing is waiting for anything else. And then we can see what the cost, the sort of overhead of the coupling is, and in this, again, sort of out of the box stuff was order 20% or so, but independent of the number of variables that we're exchanging and so on. But really the challenge for us, and we have solutions to do this, is to start to bring this line back down, and there are some quick wins on the way to do that, and then we can start playing with scalability and throwing more compute nodes at it. But this picture is really to try and show that it's a tractable problem, and in terms of getting research outputs, really you can get decent research outputs in a sensible amount of time, and really the kind of technical overhead of running an ocean model versus a couple model really isn't too serious. These are also the plots that I could have shown you, but I didn't, showing you that actually for some coastal sites you can throw as much kind of coupling at a problem as you want, but there are some fundamental sort of either local scale or sort of physics in the model processes that we are missing, and just throwing coupling at a problem in and of itself won't, depending on the problem is, won't solve all your model problems for you. So ongoing continuous component is required. We've talked about this between us as well, but this model physics challenge, now we have 3 schemes, in 4 maybe, call it 3, between our atmosphere, land surface, wave and ocean model. They all have a variant in the surface scheme and the flux parameterization in there. And we're starting to get to grips with to what extent are all these things consistent or self-consistent, which schemes are we taking into effect the currents, which schemes are we not, and so on. So again, this is the kind of detailed work that I said is now required. And then there's a question of, well, how far do you go, and what do you want to include, and what do you need to include? So this is a slide from Andy Brown at the ECMWF seminar a while ago, really asking about, well, what does complexity mean in terms of what processes do we include to be able to forecast new things versus what kind of complexity do we want to try and do things better? And that's kind of going to be a balance of research effort, computational effort, and so on. And I think there's a bit of a risk as well. Maybe hydrology is my example of this, that as you get towards more complexity, then this is a jack of all trades. It's important, first of all, to be interfacing or talking to the component experts in a useful way, but equally the onus for getting the hydrology right, for example, falls on me as a non-hydrologist to have as good a go as I can with the help of some hydrologists, for example. As we go to more complex systems, it means that us as developers, as scientists, need to have a half-decent grasp at a broadening area of work, and I think that's a challenge that we can talk about. So just to summarise, in the UK, we've got this research prototype of a fully coupled convective scale system, and we're looking at case studies now, starting to look at longer scale work to start to really be able to characterise the impact on weather forecasting, ocean forecasting, and land predictions. And we're on the journey towards more integrated hydrology. I'd say it remains unachievable, but it remains a challenge all the same. In terms of future, really evolving beyond the case study approach and work on the hydrology, we have plans to introduce the biogeochemistry, which I think is going to be a good application challenge for ensuring that all of the parts are working correctly. I think we need to go back to demonstrating that kind of natural hazard context. Ongoing challenges, ensembles, what do they look like, simulation, and then pathways towards operational implementation. I'll stop there. Thank you for your time.
So I'm thinking what we should do is take a few questions and then break for lunch. And so I'd like to do your talk after lunch. I think we all might be ready for the lunch from 1:15 to 2:15. So questions?
So on the land data simulation tools, what have you started on? There's some first order things you start collecting, just the data that you think might be relevant personally, downstream of other land surface variables. Tools have that legacy in the land atmosphere.
Yeah, so again, the land data simulation is a established kind of activity in the Met Office. So and in terms of development there, one of the things we're doing is working. You've seen it's already part of the LIST system. So there's talk about, and I don't know where the decision's got to actually, but there's talk about moving to the LIST approach for our land simulation. At the moment, there's no assimilation across any of our components. It's all sort of forecast only, seeing what the sensitivity feedbacks are. But in terms of where we need to be in the next sort of 4 years, well, I have sort of two main objectives. One is to demonstrate the evidence, and second of all, if anybody says the evidence is compelling, to have a system that's in a fit state to then start thinking about operational implementation. So it's no good me getting to 4 years' time and going, oh yeah, data assimilation, what about? So how does that work? But as a starting point, we would kind of start with wherever our operational ocean, land, atmosphere assimilation systems are. But at the moment, the land assimilation is essentially surface temperature correction with no constraint on hydrology.
Right.
Which means, and I had some fun looking at trying to route some operational outputs and looking at the runoffs from operational outputs, and they were doing all sorts. At 9 o'clock every day, it would get very wet, and then it would fall back down until 9 o'clock the next day when the system would whack a great big increment again.
The Hydrology model kind of does some of that as well. Right? So you can look at that and be correct here, that's around the soil hydrology.
Yeah. So my point there is when we start to move towards the sort of streamflow hydrology type of simulation, we can't do that independently of the air temperature, the sort of traditional atmosphere land simulation. But our thinking hasn't got beyond that really.
Yeah, well, fully coupled is sort of a branch out.
So your ocean and wave does not have the data simulation?
Not for this kind of first research work, no.
Okay, and so for the wave model in Watch 3, the level of boundary condition, do you actually have a global wave Watch 3? That level of boundary condition?
Yes. So yeah, in all of these systems, the lateral boundaries come from a global equivalent. In many of these, they're coming from the operational global system. So we don't have a simulation in our operational wave models at the moment either. Given enough resource or appetite, we could, in principle, implement the operational ocean land atmosphere assimilation next. I think one of the balances there is to try and understand what the sensitivities are in the physics before we go to the sort of fully assimilative system. So to what extent do those feedbacks still show up in the assimilation once we're in the assimilative system where we're sort of again forcing more realistic surface temperatures from the assimilation back into the atmosphere, what have you. So it'll be interesting to see what impact it has. But I think we're in the mode where we're still really testing that our system is doing the right things for the right reasons in terms of the physics. we go too far down that path.
Does this mean that you're cycling everything on the ocean or starting from the operational system?
So at the moment, we're starting from a long sort of hindcast mode run for the ocean, which again puts us in a kind of interesting place when we're then trying to evaluate relative to observations that we're starting in a close but not as close as we could be kind of state. So again, it's a lot. Our evaluation work is a lot about the relative differences rather than worrying too much at the moment about being competitive against the operational system, because it has the benefits of being initialized from the right place and so on. Part of that story is because, of course, our research work's been going on a new ocean and what was an atmosphere domain. Now that the operational systems are also in the same place as us, then we will have an operational kind of analysis to be kicking off and so on. So kind of case study work from here should be closer to operational and closer to reality.
My question is, you showed that coupling with the ocean wave actually improves mean square error. Am I correct?
Yes.
Wind speed?
Yeah.
Did you check the bias score as well? Because when you started from an underestimation of the wind speed, coupling with the ocean wave actually increased the underestimation. It's not always reflected as an improvement of the mean square error. But it's
Yeah, so a lot of I don't actually think I've got the right metrics, to be honest. In that, I think a lot of our sort of mean square errors is bias driven. And yeah, I'm not sure.
What is the native behavior of your model, your atmospheric model, regarding the wind speed? Is it understated or overstated?
It tends to underdone. Well, the main difference between our global and our high resolution though is less about the kind of overall volume of the wind. It's about the variability. Our wave watch seems to behave very well when we have a relatively smooth wind forcing. Sorry. When we move to the high resolution wind forcing, again we can there's a sort of mean, and we get pretty similar overall winds, but there's much greater grid point to grid point or out variability, and I think which is kind of hammering our scores a little bit. And that's why I was saying then the coupling is sort of acting, it's improving on that quite a bit. So it's a high resolution wind only forced wave model is particularly good system. In fact, that's why we don't use that in operation, to use a global wind forced wave.
All right, so here's the plan. We'll break for lunch. Let's take it until 2:30. Give people a little extra time to chat over lunch. Come back here at 2:30. We have 2 more talks. That will take us to 3:30, and then we'll still preserve an hour and a half for discussions and breakout. So